right, great. I want to first introduce you. I really appreciate you calling in. Lisa is a lecturer of computer science at Stanford University, so she's not too far away from us, where she teaches probability and computer systems. She completed her PhD at Stanford, where she studied and implemented tools for understanding students in computer science classrooms. Today, she's going to talk about learning networking by reproducing research results. And although I didn't get to see your original talk, you were at the reproducibility conference that Evo had put on, I guess, over the summer. And that was one of the interests that, Carlos and Evo were really interested in the work you did. So we were really happy that you were able to join us today. And I'll let you get started.
Great. Thank you, Stephanie. I'm actually, I'm really excited to be here. So yeah, I mean, I know it's always difficult running a virtual conference, so I appreciate all of this. But today, I did want to talk about this particular topic. Now, a little bit more background about me before I started my talk. Since I did my PhD at Stanford, I actually started in computer networks. And I worked very closely with Nick McEwen. And then over time, I've really moved towards researching education, where, I mean, instead of networking systems, now we're networking students together and networking teachers as well. And so as part of this, Nick and I really worked together to use Stanford as my research test bed in education. And I've been working specifically on networking education at Stanford in part, where we have 2 classes, Introduction to Networking and Graduate Networking. But today, instead of talking about research into specifically open source systems, I wanted to talk a little bit about how we teach students to interact with these types of systems or to feel motivated to be part of these types of communities. And I'm going to do this in the context of networking, but it can really be expanded to these other domains as well. So let's first start out with a small scenario. Let's envision ourselves as like some fledgling networking instructor. Pick your favorite institution. Let's say I pick Stanford, and you're just starting out in your career and you're very excited. The Department of Computer Science, the chair tells you that you need to teach this class called Graduate Networking. Okay. And so you teach this class and you say, okay, well, I know how intro to networking is going to work. I pick a textbook, I teach them about whatever number layers of the OSI you want to tell them. And that's kind of it. They implement maybe a router, but it's pretty fixed overall. Now for graduate networks, it's a little bit more open-ended. You could give them a more involved textbook or more advanced textbook. You could have them read a whole bunch of papers, but what's really unclear is what types of projects would help someone who is learning networks at the graduate level. And so what we thought about when we restructured this a few years ago, we thought about the following goal. I just wanted to open chat to make sure I'm not messing it up. Okay, thank you, Stephanie. Yeah, so I thought about the following opening goal, which is I'd like to train and build experience for these students in order so that they can become a future networking researcher or networking engineer. And I wanted to highlight this word experience here because it not just only includes technical skills, but it also includes things like communication, responsibility, and just general excitement for looking at networking or systems as a whole. So then we thought a little bit more about this and we said, okay, well, what kind of systems should we actually allow our advanced students to build? We could either give them the same project. We tried this for a few years. This is a little bit boring and it doesn't really allow us to account for that creativity that I suggested earlier. We could also have them create their own project, super creative, very exciting, but also very risky. If you're working in the 10-week quarter system, much like Stanford is, then, well, this is pretty difficult to do in a way that kind of motivates students to continue on in this field. So what we said instead is, okay, what do we have available to us? We would like our assignment to be such that students can build a system, and they should be able to also think critically about the system as well. So circa 2012, when we were first thinking about this, well, this was the beginning of MiniNet, which is a realistic network emulator that is still used in a good amount of industry and research today. So what we said overall is to say, okay, how about our assignment will be to reproduce someone else's research? Okay. So this is what we decided to do. And how was our experience overall? So we've offered this particular research project for the last, since 2012, so for the last 8 years. It's been a really, really cool experience. Because what we found is 3 big parts about this project. It sparks these cool discussions that would never have happened otherwise between researchers and new students. It gives these new students more tools to use in their own research. So oftentimes, the students who take the graduate networking classes are first or second year PhD students, and whatever systems, whatever tools they learn in their classes are ones that inform their thesis work. And then finally, it just tends to jumpstart careers in networking. So over this talk, the next 30 or 40 minutes or so, I'm going to give you examples of all of these different things. And then finally, our last goal really is to build this, excuse me, more Zoom. Okay. Finally, our last goal is within these 3 projects, there's a larger goal of contributing back to the research community. We'd like to provide a fully reproducible project created by the students in the public domain. So whatever the students create as part of their projects, they can share it back with the community. So as part of today's talk, I'm really going to focus on 3 parts here. There's going to be a project overview where I just give you the lowdown of when this project happens and how the project happened over the past 8 years. I'm also going to share some student stories, about 4 or 5 of these or so, where you'll kind of see all these different cases. And then finally, we'll talk about greater impact. And so really, the takeaways here, just to give you the main bits so that you understand what we're going into. You'll find that these projects really beget creativity in how you actually end up reproducing or replicating some of the results, just because of the resources available to the students. The student stories kind of reveal that reproducing research largely depends on how available the original artifacts or platforms were, and things change over time as we develop software and systems. And then finally, the greater impact, like I've alluded to before, is really a way for students to learn how to be productive, how to be proactive, and how to engage with software and research overall. So as part of this, since it is going to be a live recording, I'm just going to be going through the talk, and I'll be happy to answer any questions through the platforms that Stephanie mentioned after the talk. So just bear with me that it won't be, since I'm not pre-recording it, that will be the format, similar to a normal talk. Okay, thank you. So let's start with the first one. What exactly was this project? Well, you take this 4-week timeline, where this is towards the end of the class. The first 6 weeks is them reading papers and understanding some smaller assignments, maybe how many networks overall. And within the last 4 weeks, let's say from week 6 to week 10 of a 10-week quarter, at week 6, they do a project proposal. They usually pair up with a student. With another student, they have some intermediate report along the way. They have the final report, and then they have some sort of peer discussion or presentation. Now, as part of the project proposal, students pair up and they pick a paper, but not only do they pick a paper, they pick a key result, so a key figure or a key table to reproduce. And then as part of the project proposal, we tell them that the first step is to contact the original researchers, say, hey, I'm doing this project, just letting you know, but also do you have any advice or resources that you can offer? As part of the intermediary work, well, students just have to show that they've been progressing towards the result. And then furthermore, there are some TA student meetings at this time for next steps, or perhaps to encourage the students once more to contact the original researchers or to loop the teaching staff into that conversation. As part of the final report, like I said, because one of our goals is to push a public version of the code into the public domain, we have the students post a blog post and a public source code, and also steps for reproducing the students' results. And then finally, as a peer discussion, we often have in-class peer presentations or some sort of peer review that happens on our blog. Over many, many years, we've had a lot of different research venues that the students end up picking. We give them a starting list of papers and conferences, and it turns out that, well, out of these, the most popular ones are NSDI and SIGCOMM, which are, well, the 2 of the top networking conferences overall. But there's many things as well. So there's things just like security, systems, internet standards, and so on. So there's a really diverse set of research venues. And there's even more diversity in the experiments themselves. Some of these are actually inaccessible to people outside of the institution. So for example, there are many there are several top research articles that are based on Google's B4 network or Facebook's node cluster of 2,000 nodes that's often inaccessible to students, especially if they're not interning at these companies or working at these companies. There's things like NetFPGA programmable solutions, which often have a longer timeline than can be satisfied in a 10-week quarter. And there's also theoretical models as well. Various other things. So there's a good amount of research that actually does these traffic studies of how the World Wide Web traffic is, just measuring traffic on the World Wide Web. And then furthermore, there's a large plethora of network traffic simulators and emulators that are used as well. Okay. Now, the students only have 4 weeks. Furthermore, they often don't have exactly these resources to these larger companies. So one of the challenges that we had to deal with up front was how to reproduce research with these limited resources in a way that could guarantee some success for students. So the first thing that we decided up front was that we would like to use simulators and emulators where necessary. So instead of focusing on a lot of these large network solutions or hardware solutions, we encourage the students to try out things in these emulators and simulators like EmuLab and NS2 and MiniNet, like I mentioned before, and also Mahi, which is developed at MIT. And furthermore, since the students themselves are internet consumers, they had access to a good amount of the consumer side measurements that were taking place on internet traffic. Yeah. Now, if the students did indeed have access to hardware, we definitely encourage them to do so. So especially like these programmable chips, but we generally said, hey, these simulators and emulators are available to you. And then furthermore, you can use these cloud computing resources that are accessible at the education level to actually run these types of experiments. So over the past few years, I think Google and Amazon have really increased the accessibility of their cloud platforms to young researchers, to educators as well. So we've been really making use of that and enabling our students to run these larger experiments. And then finally, the third tip that we told all the students and that we just kind of established up front is, again, ask the original authors. And the reason why we did is because if you took a look at what networking research generally entails, there's either some sort of system or platform, and then there's also some sort of workload or experiment on which they perform or on which they measure their system performance. So on the system source code side, well, there's a lot of different options for the students. And this is what's been recorded over the past 6 or 7 years. About, let's say, what is this? It's like about 60% or so is in some sort of open source, but then out of that 60%, maybe only about 30% is still actively updated and available for current use. The rest of it is a little out of date or inconsistent. But something that's really important here to notice is that so 10% of the time, or rather 7% of this time, students often did need to contact the authors and be like, hey, I don't actually see your system anywhere. Do you mind sharing it with us so we can provide a version of this back to the community? And the authors most often said yes. Now on the workload generation side, this is also relatively interesting. So if you imagine again that you have some system, you need to measure the system against something, some sort of workload. About 20% of the time, this workload was open source. And 40% of the time, there were sufficient details in the paper. But then the rest of the time, the student said, there are some details, but not enough. So I'm going to generate the workload and assume that this is as representative as we can be to the result. Now, so that's the general overview of the project. It did end up being quite ambitious in terms of us thinking about it back in 2012, but our students have achieved lots and lots of things. And so for the next part, I'm just going to show you a little bit about what the students went through. There's a variety of research topics kind of reflecting the variety of networking conferences and systems conferences that were looked at. Things like congestion control, TCP, to video streaming ended up being quite popular. And then also things like topology of data centers was heavily studied. More recently, there have been there have been various projects around Spark and these sort of distributed data systems. And overall, we found that, well, there were 73 unique published papers on which we did this reproducible research project. So out of these 73 papers, there's actually been 150 projects or so. So it's a good amount of projects. And we have kind of a timeline of the successful or unsuccessful projects over time. So at the very top, there's 2012, all the way down to 2019. 2020 is cut off in this particular graph. But you can see that most of the students are successful. Why are students unsuccessful? There's a variety of reasons, but one of them, for one, in 2016, we introduced not just MiniNet, but also the Mahi emulator, so the existing MIT project, and students just had a little bit of difficulty running with that and figuring out, and on our side as well, we also had to figure out what projects were useful for that emulator. And then in 2018, there's kind of this jump of unsuccessful projects. That's really because we kind of required students after this point, after reading the same papers over and over again, we required them to research new things and continue to create publicly reproducible projects for new projects. Now, as part of this, so post 2018, I've kind of, again, highlighted them differently, but you can see that some of the top papers that were reproduced, prior to this 2018 guideline from our course staff was as follows. So there's a lot of things involving TCP. Naturally, because TCP is part of the Linux kernel, and so it makes it quite easy to measure experiments on to run experiments on that. There is a Jellyfish, which is a networking paper that involves a good amount of simulation. So this was quite popular. And then furthermore, video streaming, which is a story I'll talk about a little bit later. This one also was quite popular. So let's get into it. Our projects really had students learn a lot about engineered network systems. And so for the next part, I'm going to show you how this really depended on the availability of a lot of these systems, but students got a lot out of all of their stories. So as part of the first project, I just wanted to give a quick refresher to those of you who may not have seen congestion control recently. So as you recall, one of the big things about networks is that there's this thing called TCP. And TCP is a congestion control algorithm where there's a sender, they send data packet to some receiver, and then in TCP at least, the receiver sends these acknowledgement packets back whenever it receives a data packet. And network congestion is something that we would like to avoid, which is this congestion is this problem where the network link is overloaded and there's no longer any useful communication. So what TCP does to try and avoid this problem is it has this additive increase, multiplicative decrease algorithm where it sends acknowledgements back and slowly increases the amount of packets it sends out. But then as soon as there is a data loss, it halves the window or decreases the window by a multiplicative amount. Now, the reason why I talk about this and the reason why I gave this refresher is there's this thing called this TCP optac attack. So as part of this, you could optimistically send a whole bunch of acknowledgements to some senders, and then these senders could be like, great, I can just continue opening up my window and send more and more packets until there's so much congestion in the network that, oops, and then the link goes down. So this is an attack that has been measured over time. And as part of this research, Robert Sherwood in 2005 kind of really measured how the amount of useless bytes in the network really increases exponentially based on the number of victims who are optimistically sending, or excuse me, who have received these optimistic acknowledgements and are sending more and more traffic over time. Now, what do students do? Let me show you how this works. So Robert Sherwood actually did their original work in the NS2 simulator. So it's a sort of, hey, this is going to be the numerical possibilities. But what our students did in 2016 is they emulated this traffic. So they actually are on MiniNet, they opened up to 64 connections, emulated, and over an emulated link, and then they were able to kind of send a whole bunch of traffic. And what they found is that over time, because of the size of their the EC2, the Amazon computing instance that they were using, they couldn't actually see that exponential growth in traffic beyond, say, what is it, 8 victims here. but they still achieve the same shape. And so we would actually consider this a successful reproduction, because again, it shows something very similar to what the graph is showing, minus these computational limitations. Okay, so that's pretty cool. So let's put a little check mark here, because this is what we would consider a successful one. Now, here's an interesting one, which kind of shows the availability of these artifacts over time. So something about video streaming that was heavily studied in 2012 as part of Taiyuan Huang's thesis was that there's this idea of video streaming is that you really share the network with other flows, with other connections. And so oftentimes, because your connection is very, very long lasting, you are often very conservative in how much you contribute to network traffic. So in this particular case, we would have some great throughput for a while, and as soon as someone else jumped onto the network, we would immediately throttle our connection and have a very, very bad rate. Now, there's this thing called Netflix, and what Netflix ended up doing is, well, it exhibited this exact characteristic. So this is something that this original paper studied and observed as an issue. Now, in 2013, the students were able to reproduce this result, essentially by saying, all right, well, or rather they would like to reproduce this result, and they said, okay, our experiments are actually going to really use Netflix. We're going to try and recreate this exact experiment where we connect or watch some Netflix video and then connect with some other throughput. And we want to see this throttling that happens with Netflix. We're not going to use any sort of mini net. We're going to use the real system because we're working with web applications. What did they see? They saw something slightly different, which is that now, instead of having the service A client, which is Netflix in this case, instead of having that client immediately throttle, what Netflix did is it actually ended up sharing the network correctly with the competing flow throughput. So students were like, hey, what gives? So they messaged the original author, and what they said is, they said, hey, we've actually observed that the problem reported in the paper has since been fixed in this particular platform. And so we've contacted the paper authors, and they confirmed that this is the case. Actually, Taiyuan actually works on Netflix now, and she was one of the people who fixed this problem. And so it's actually impossible to measure and observe this thing on the original platform for which this paper was run. Anyway, we still put a check mark next to it because, you know, they were really trying to reproduce the experiment, and they got as far as they could, and they were able to confirm with the authors what happened. Here's another interesting story related to the Netflix time. So again, this paper was actually reproduced multiple times by different authors. And so what we found is that in 2017, so what is this, 4 years later, 2017 students decided that they wanted to replicate this experiment instead. So instead of reproducing it on the exact, on trying to use the same platforms, try to see whether it happens on other platforms as well. Vimeo and YouTube, which are freely accessible without some sort of subscription. On YouTube, they observed that YouTube does not exhibit this downward spiral effect. So similar to the 2013 students, they saw that YouTube did actually share the traffic quite well with another competing flow. But on the other hand, Vimeo did have this original result from the 2012 paper. So again, we would consider this as a success because the students kind of explored this, these options and identified when things would match up. So that's pretty cool. Now you might be thinking, well, this is great. There's a lot of check marks on the page, Lisa, but what about unsuccessful research reproductions? Because they must exist. I saw those blue bars earlier on the graph. And you're right. So there's a few common scenarios as to why this may be. Oftentimes there's overambitious engineering. The students, this is oftentimes their first time running some sort of systems research project. So for example, when the students wanted to implement a mixed linear programming optimizer, they spent their last week just trying to find a freely available one or one that had a very low subscription service. And so they were actually unable to implement their original system. Other unsuccessful scenarios include ones where there's a small difference in the workloads. So for example, in this particular case, there were some, this study was to figure out whether there were Wi-Fi links or international links. And overall, they found that actually the measurements of quality, their measurements were much higher than the original paper reported. And so there was actually it was very difficult to reproduce the original result to begin with. And then finally, the last one is alluding to this this idea that we saw in the TCP optac scenario, where there was just some sort of restriction in the emulator performance such that they could not reproduce even one small part of the results. So in this particular case in QJump, they tried scaling down all of their parameters, but they still couldn't even achieve even one of the target latencies. And so they were unsuccessful in this regard. However, this is still a productive part of the research experience. And so we did still value these students' contributions. Now, here's another question that might be running through your minds, which is, how does time affect research artifacts? Okay. So as you can imagine, actually, a lot of those conferences and journals that were listed back in slide 7 or so were actually from, or probably spanned a very, very long amount of time. And some of the research is actually from, say, 10 or 15 years ago. So there must be some element of time that is actually influencing how these students reproduce their research. And it's true. So I'm going to show at least 2 cases here where I give 3 examples overall about how these Linux kernel versions, despite Linux being an open source system, actually kind of interferes with at least our students' ability to replicate the research. And then furthermore, the evolution of web traffic over time has really impacted the reproducibility of these results. So let's talk about Linux kernels first. Proportional rate reduction was an algorithm to pace out retransmissions across receive acknowledgements. So this means that for TCP, oftentimes after you halved your window or decreased your window, you wanted to retransmit some of the data loss. Well, instead of retransmitting and immediately opening up or immediately halving down, you could kind of decrease and then retransmit a little bit at a time. So that's what PRR was. And this was back in 2011. Now, back in 2011, if we take a screenshot of the original paper and post it onto the slide here, the author said that they were going to be releasing this in an upstream kernel. So PRR is going to be part of Linux. And indeed, that's what we saw to be the case. So in 2011, there was no PRR, but 3 years later, the Linux kernel, and especially Ubuntu, actually shipped with PRR. Now, it's back in 2015 when they actually analyzed this result, they saw, hey, these 2 additional discrepancies between those versions of 3.0 and 3.2, they actually don't have an impact on the experimental results. They were still able to identify and reproduce the results at this time. So that's what 2015 said. But then over time, well, in 2016, it turns out that Linux shipped with the option to turn off PRR. So perhaps PRR was not as useful or at least not as widely used as was originally thought. And there are 12 commits between 2011 and 2016 that reference PRR and how to update it over time. But then in the present day, so this is 9 years after the original work, there have been 365 different changes to this one file in the Linux kernel. And so you can imagine that as part of this evolution of the Linux kernel over time, it makes it very, very difficult to kind of extract away exactly what the original authors were working with. And this is something that our students often ran into as an issue. Now, on the other side, I did want to give 2 examples about web traffic, since it is largely dominating the application side of network research in the past few years. One of them that I'd like to talk about a little bit is HTTPS. So for those of you who recall, HTTPS is a way of making connections more secure by providing certificate authentication on top of it. And so back in 2014, when HTTPS was first introduced, it was studied and measured that page load times were slower than HTTP on fiber, so on networks, on local networks, or on 3G, so on mobile networks. And in general, just to summarize what this graph is saying, essentially it says that for 40% of sites, having HTTPS made it noticeably slower compared to the HTTP option. For 55% of sites, there was about no difference. And then for a very, very small fraction, HTTPS, the secure version of HTTP, was slightly faster. Now let's jump ahead to 2017. So this is just 3 years later. The students actually saw 2 different graphs. I mean, you might have a question, why didn't they just put it on the same graph? They wanted to put it on 2 different graphs. So that's what we have. So on the left, on the middle graph here, we have the fiber measurements as of 2017. And on the right graph, we have the 4G measurements as of 2017. And the students saw the following. there was actually now only 15% of sites where HTTPS was slower. And for the large majority of sites, there was really no difference between running things on HTTP or HTTPS. And then furthermore, if we will study the 4G graph here, for 30% of the 4G systems, HTTPS was actually faster for a lot of these web pages. Now, why may this be the case? Well, there's several reasons that the students kind of studied, because they said, wow, this is completely different from what the original researchers saw. And so as part of their analysis, they said that in the time since the paper has been published, HTTPS has drastically changed. So back in 2014, almost all traffic was really small, privacy-sensitive objects, but really now, at least in 2017, and then now even nowadays, it has become the norm. And so in 2014, YouTube was just beginning to add HTTPS onto their video streaming platform, but now again, it's the norm. So essentially, if you consider how web traffic has changed over time, we expected these things like certificate verifications, improvements in how network speed and latency work overall to really just reduce the overhead costs of HTTPS. And this is something that our students who are first or second year PhD students or master's students were able to analyze. And this is quite impressive. There's one more result that I just wanted to show you about how web traffic changes over time. So this is TCP Fast Open, which is just saying that in 2011, when the original research was studied, if we had this thing called TCP Fast Open, which would quickly open the connection and allow for transmission, it would really increase the page load time. So, I mean, we'll really increase really from 2.6 seconds down to 2.34 seconds for the Amazon page, for example. But then now we look at 2015, so this is just 4 years later, we see that, okay, there is a larger difference in TCP Fast Open, so it is doing more, that's great. But what's up with these load times? Why is Amazon taking 15 seconds to load? Okay, and in fact, this actually might be milliseconds, so I'll double check that. But let's take a look at what 2011 Amazon looked like. Let's take a look at what 2015 Amazon looks like. Actually, this is 2020 Amazon. So as we can see, the nature of these websites on which these a lot of this original research was doing their studies on, the websites look very different today, even if it's the exact same website. And that's also something that the students were able to discover as part of their journey towards reproducing research. This is very cool stuff. And there are many, many more stories, and I do encourage you to actually visit our blog to see all of the studies over time. But right now, I just wanted to pause a little bit. Because a lot of you may be thinking, well, this is great, but so what? These results, what are they doing? Okay. And so the last part of my talk, I just wanted to focus on the greater impact that we believe that this sort of educational project has on preparing students for a career in research or in industry. If we considered what we had to decide back in 2012 versus what we do now, we had this choice of giving them all the same project or having some open-ended project or reproducing someone else's research. And what we found is that our student mindset changed from, hey, I'm not sure how to take the first step into research because I'm just doing this one very small project that is in this small ecosystem of the class. And now our students have really changed to thinking that, hey, I am making valid contributions, and furthermore, I'm making them to an active research community. So people care about my work. And so what do I mean by people caring about what our students do? Well, you can see that our student, as our student is described in this particular project, actually interfaces with 3 different parts of the community. The first one is the original researcher. So that's the person who, that's part of the team who originally made that research work. The second one is a new researcher who may see the student's work as posted on our blog. And then finally, the last one is the actual tool developer, the platform developer, the simulator, emulator developer, who the student may have to interface with to achieve their results. So let me show you a few examples of this. In terms of contacting the original author, in this particular case, there was this was a adaptive wide area streaming network to kind of show that, hey, if we were adapting to wide area networks, we would do better in terms of throughput and latency compared to regular TCP. Okay. And so the students' results kind of show this, at least for latency and accuracy, they're relatively close. But something important to note is that as part of the acknowledgements in their blog post, in their paper, they said, hey, we would like to thank Ben for all of the work that he put in because and who is Ben? Well, Ben is the first author on this paper. But furthermore, I mean, the students in their blog post said something like, okay, overall, we found the documentation to be outdated and at least at times misleading, quite a scathing remark. But we did rely mostly on close reading of the paper and email correspondence with the original paper's authors to really achieve this goal. So what does this mean? This means that the students really kind of saw the researchers as these humans, as these people that they could interact with to achieve their results. And this is productive for the original researcher as well. Now, other things here. So if we took a look at another case where there was a lot of interaction between the student and the author, we can jump to a Q-jump. Which no pun intended, but here this is a different story. It was a successful reproduction compared to the other Q-jump one that we saw earlier, where the students, as part of their work, said that in this Q-jump work, they actually, the researchers, as part of the original Q-jump work, actually had, as part of their release of the work, steps to reproduce the experiments. Now, the students took a look at this and they said, hey, yeah, the assumption is that these results will be reproduced in an actual data center, but we don't have a data center. We only have Mininet and we only have AWS on which to emulate this traffic. So what did they do? Well, they took a look at the scripts, they took a look at everything that was available on the website, and while they didn't use the scripts directly, they kind of appreciated this gesture, because obviously as students, their goal is to reproduce the work, and at least having something to start with was quite wonderful. And then furthermore, after this particular research, since the original authors were aware, they actually tweeted about the students' reproduction of this work, and so it's quite engaging to see that overall for the students. So, so for the original researcher, what do we see are benefits? Well, they can improve and confirm their current and past research and kind of provide this context which they would benefit them to revisit their work over time. Now for the students, they kind of have two things that they find out. One of them is that they can implement specific tools to further their own graduate research. So in the Q-jump experiment, there was actually a scheduler that one of the students had to write, and she actually used that scheduler as a key part of her thesis work a few years down the road. But then furthermore, for most students, it's just to realize, again, that researchers are real people. You know, like you send an email to someone, there's some probability that they will reply. And when they reply, it's actually quite informative. And so you actually get a lot out of that. Now, why does the student interact with the simulator and emulator developer? Well, a lot of this could be for tool feedback and development. So recall again, back when we started this project, we were first working with Mininet and starting that up. And so actually this project helped to just provide a plethora of examples on which Mininet could or could not work. And then when we introduced Mahi Mahi in 2016, this is a way to, again, to provide examples of traffic or research projects on which Mahi Mahi could or could not work. And so for the could case, that is incredibly beneficial because it allows these tool developers to see where their tool goes over time and to kind of tailor their adjustments towards these projects should they be fruitful. But then what we saw for students is that there was an additional benefit, which was that for this particular student, immediately after this class, she actually got a job at a large company for that really just focused on these sorts of emulators. So by having this prior experience of working with an emulator and actively working with a research project, this fully prepared her for what she immediately jumped into in the real world, which was a deep dive into the Linux kernel and into Mininet. So she was ready. And then finally, for new researchers, what do we see? Well, because we're pushing this fully reproducible project into the public domain, we find that other researchers can indeed build on it. And it kind of eases this technology transfer because, well, oftentimes as a researcher, what do? You see what other people have done. You start with that as a baseline, and then you keep going. And then now, in this case, we see what a new researcher can see what other people have done, see what the student has done, and then reconcile these two experiences, these two experiments, to further their own work. So what we saw in one case is that this particular student and her partner worked through a particular project which did not have an open source platform available, and so they actually wrote their own platform and then posted that as part of their work. And they were and so this group was actually contacted by both the original authors who said, hey, thanks, this is awesome, and a master's student who was working on his own research as a way for really the student team here to become another pillar in the community for this particular work. So I believe this is actually a workshop paper, and so naturally it did not make sense for the original researcher to have published his work in some form at the time, and so the students are really helping both parties here and learn from them as well. So to close, I really just wanted to think about a few things, which is overall I've really just talked about networks. And the reason why is, again, because we were dealing with a graduate network course, and we wanted to figure out a way to teach students this idea that they could engineer a system, but that they also can rely on people in their community to help them engineer a system. They're not starting from scratch. And then furthermore, they can contribute to this community. Now, in other fields, we actually have seen that this idea of reproducibility is very common, let's say for machine learning classes or artificial intelligence classes, where a large portion of those classes have some sort of project at the end where you either create something new or you try to reproduce something that is existing that is quite daunting. So there are a few ways to go beyond this, but I just wanted to think more broadly about this. Because really, I think one of the key takeaways of this talk, and then furthermore of these past 9 years of work, is that while we did want to answer this question of how to teach students graduate networking, there's this larger question of how to create an ecosystem of research that really supports future innovators, but supports them by encouraging them to participate in the community itself. And so I think that this work is really just one example of this, about how we could encourage this reproducible research that's led by the community. And so this talk kind of uses a lot of students to go towards reproducible research for all, but that's kind of a thought that I wanted to end on, is I think this is actually a really great perspective that we can teach our graduate students before they go into the community as a full-time person. So that's the end of my talk. I just wanted to thank my collaborators. So Nick McEwen, Keith Winstein, Sachin Kati are all regular instructors of this course, and Bruce Bang is their current graduate course assistant who greatly helped me with getting some of this data. And so thank you. Yeah, I think we have a few minutes, so I don't know if we can take questions or what it would look like.
Great. I think we had a couple questions already on the in the minutes. The first one was from Philippe Krief, and it said, do you know, who's from Eclipse Foundation, do you know how many students became active contributors to the OS projects they studied?
Yeah, good question. So now I have the minutes open. Thank you, Stephanie. Okay, cool. So I can probably read them as well. Okay. Yeah, so Philippe, I'm not super sure. So a lot of these studies were done passively after, and so I did a few interviews with the students after this work, and so it's a little bit unclear, but oftentimes the students tended to choose projects that they themselves were interested in or they were tangentially involved in, especially if the research project was coming from Stanford. And so we did at least have a few students who were already naturally part of that ecosystem of, say, reading the Linux kernel, trying to push a few changes to that. So I think we could do a better job of encouraging students to make changes. But as part of this, we really were just saying, hey, this, at least from this one data point, you are able to contribute, but we didn't study after that. Now, Ivo asks, in the context of networking experiments, is there any sort of experiment manager or similar tool that you could see which would make it easier to share not only code, but all the other artifacts associated with original results? This is a good question. I mean, I think this is related to Evo's work right now with Popper, but we don't really have an experiment manager as of right now with networking, and I believe that is because there's really like a plethora of different platforms on which students and researchers alike kind of share their results. So what we've tried to do is at least have the blog, which historically you can see what papers have contributed results over time. So we've been trying to do that organically. But I mean, I know like in, say, artificial intelligence or like the machine learning community, they also have Docker. And for many of these experiments where they have these sort of test beds these like contests and challenges, they are able to have this larger repository of people who have all done things on the same data set and achieve certain results. And so I imagine that if there's an analogous version of that, where here is this see-all end all of data set of, say, network traffic or something that you can test anything on, then that would be a useful repository on which people could share their results back to the authors. But I mean, again, I think in the context of networking as it is, because of the large changes in web traffic over just the last few years, it is quite difficult to have that sort of comprehensive network traffic data set if we were to make one. That would be representative of traffic for a good amount of time.
So can I follow up quickly on that?
Yeah.
So are you referring to these or like catalogs, like papers with code where they show all these, or
yeah, I'm referring to
OpenML where you have all these.
Yeah, so I'm referring to things like ImageNet, or like these sort of larger challenges where you every year or every half a year as part of a larger conference or something, they release this sort of, hey, try your best on this network data or excuse me, on this image data or something like that. And then the image data, I mean, because they're images, I mean, perhaps the nature of the data set is such that it doesn't change over time too much, and it's kind of still okay to create new applications on the same image set data. But I believe that sort of data-based repository where we could amalgamate a whole bunch of research on networking and a whole bunch of performance results on networking would actually be a little bit difficult, just because the nature of, say, if we're just dealing with web traffic, the nature of web traffic is that it changes every 1 or 2 years anyway. And so it'd be difficult to do that sort of representation. So I think whatever would have to be created in the sort of experiment manager would have to continue to be updated, or I mean, rather either continue to be updated if it was for web traffic, or it would have to be something that kind of was observed over the past 5 or 10 years, such that the data that you're working with is still representative half a decade down the road. Yeah, so I think that's a challenge that perhaps maybe might be specific to networking. And specific to the types of, like, the way that networking has changed in the past, recently. Now there's another question, I'm not sure who this is from, but for container technology, were there any experiments using containers? If there were they easier to reproduce? This is a good question. So I can recall perhaps 1 or 2. Now I think containers are more recent, and as a result, because this is usually the class that students take immediately after taking the introduction to networking class, they often haven't taken other systems classes yet. And so for a student who is like getting first introduced to this idea of graduate systems study, they actually aren't aware often of containers. So I mean, I think that is also changing. So again, it depends on the course content, and I believe that our course is trying to figure out how to, always balance the historically important parts of networking research with the more up-to-date research that involves several different systems. And so I hope over time that there will be research involving containers, but I don't have any anecdotes that I can point to right now. And then finally, a last question that's at least on the minutes that I can see. Do I have statistics on the number of experiments using NSF test beds, Cloud Lab, Chameleon, and so on? Yeah, this is also a good question. So we don't actually have many of them. And I mean, that perhaps is just because we really did encourage students to use MiniNet and Mahi Mahi, which were two platforms for which we knew the developers. And so it's a little bit easier to have, we already had that rapport. And so it was a little bit easier to encourage that. But we did have some students say use EmuLab or these more, these larger communities, which would require some sort of subscription service. And I think what we found is that because it wasn't readily accessible to us, there was just a little bit more warm up to being able to use that platform. So I think over time, if we did have readily available NSF testbeds, or if we had researchers that were actively using those testbeds, it would be easier to get the students on the ground running with some of these projects. So yeah, so the answer is no statistics on it. It's very few, if any, and perhaps we can definitely change that if we had people who were connected in the teaching staff to this this community. Yeah.
All right. Are there any other questions for Lisa? If not, it's right on time. Wrapping up. Thanks a lot. Thanks for the talk, and definitely interesting. This talk was recorded and that included all the Q&A afterwards.